Okay, I believe we are now recording. So thank you all for joining this morning. Welcome on behalf of the AI Hub for Science in the College of Sciences and the Research Facilitation Service. We're going to do a session today on GPU availability here at NC State. There'll be a little bit of a demo, and then we'll have a Q&A session. We'll go through GPU resources that are available through NC State's HPC cluster and a service called NC Share that is based out of Duke. So thanks for joining us. As I just mentioned, our goal is to help you better understand what advanced computing resources are available to NC State researchers to help accelerate your research. And to start off, we'll do a welcoming and a couple of opening remarks, maybe talk a little bit about who we are and how we can help. We'll give an overview of NC State's HPC, as I just mentioned, an overview of NC Share, and then Derek DeVries, our research integration consultant with the Research Facilitation Service, is going to talk about choosing those GPU resources and how to access NC Share from here at NC State. And then Dr. Vladimir Skokov and Dr. Paul Liu will talk a little bit about their research use cases and how they've used NC Share to accelerate their research. And we'll open up the floor for some Q&A and any discussion. And hopefully we're going to pack all of that into 2 hours. Wish us luck. All right. So Paul, you want to talk a little bit about the AI Hub for Science?
Yes. Hello, good morning. And I want to say a little bit about our newly launched AI Hub for Science. As you can see here, you can access this website through the Science NCSU College of Science. And our vision is to position NC State as the national leader in AI-enabled scientific discovery by, uniting everybody together, research, educator, and empowering innovation and transforming how science is conducted, taught, and applied for society benefit. And of course, we can do so many things. Like foster incorporation, interdisciplinary collaboration, and support large-scale ground proposal development, and training, promote responsible ethical using. And for example, we plan to have a distinguished AI Speak series, and also AI Hub faculty fellowship, and training workshop, ground proposal, AI literacy improvement, and cyber AI security, and ethical responsible user, and also develop industry and government and global engagement. So, for example, in next month, and we will talk about the time series large language model. So, because how we can implement the time series data, this is the kind of a key. And also in end of August, there will be a training, a one-day intensive training. We collaborate partnership with Triangle Research AI Society. This is how to build and fine-tune a small large language model. And from beginning, understand the architecture, the framework of the language model, how to prepare the data, how to pre-training one, and how to fine-tune one, how to do a reinforced learning, how to low-rank depth training. So everybody come back home, we'll have a small language model. You can work in a local environment. So this is the pipeline we go through from 0 to 1. And of course, for 1, you can reach 100. So that's kind of an event. We partnership with the community. So you can take a picture and they have a QR code. I can send an email if you send me an email. So this is the opportunity. One day, if you invest yourself one day, it will be different. And this we try to do. And also we have a whole bunch of distinguished speaker series. For example, NVIDIA will come here talk about October. And there's a director work on the Earth system modeling. And also we have a Google DeepMind. Their group leader will also come in here. We haven't fixed up a date yet. They have agreed to come here to join the AI Hub Distinguished Speaker Series. And also we have a social media LinkedIn account. And so this AI Hub just launched. Emily in the back, Emily there, and we are co-director. So if you have any questions and you want to working with us, we will be happy. So that's all about AI Hub for Science. So we are working together. Thank you.
Just very briefly about the Research Facilitation Service. I know y'all shared where you're coming from on campus with us before coming today. And so we have a lot of folks from, for example, College of Engineering. So you may not have heard of the Research Facilitation Service yet, but we are a joint effort on the part of University Libraries, the Office of Information Technology, and with some support from our research office. And we act as a first point of contact or a one-stop shop for folks who have questions about research, computing, and data. So we are there to help with those needs throughout the project lifecycle. We can start helping, we can provide assistance as you're planning for your project, to budget for resources, identify the appropriate resources, kind of think through how to get set up with your research computing workflows. We can also help you once you've already got those set up to troubleshoot or find better resources to support what you're trying to accomplish. We like to think about ourselves as a good place to start when you don't know where to start. We have been rolling out across campus. The service started in 2022 and has been rolling out across campus ever since. And we've been doing it on a college by college basis. So we are formally operational with the College of Sciences, Natural Resources, Humanities and Social Sciences, Ag and Life Sciences, and just this past semester we extended to the College of Education. But we are willing to help folks from wherever you are on campus. Please just feel free to reach out. We are a free service for all NC State affiliates, and while we prioritize assistance to faculty, postdocs, and graduate students, we know that there is, and we sort of are designed to support the research enterprise. There's not a bright line between research and teaching a lot of the time. So please do feel free to reach out with us with your questions, to us with your questions, and we're happy to put you in contact with the right people if we're not quite the right fit. And you can get in touch with us via our website. It's very easy. We have a brief contact us form. Just tell us a little bit about what you're working on. We'll be back in touch within 1 to 2 business days to ask for some more information or to point you in the right direction. Just a couple of quick logistics for today. We're going to try to keep questions until the end, but if something isn't clear, please feel free to interrupt and ask. We'll be monitoring the chat online as well if folks participating remotely have any questions. We have not built in any breaks, but please do feel free to get up and move around as you need. You are here in this room 201. You probably saw the restrooms on your way in, but they are right down the hall, and there is a water fountain there as well. All right. I think with that, we'll go ahead and get started. And I think Andrew is up first.
Okay. How's everyone doing? I'm going to talk about
Presentation.
Actually, I want it like this, but I'm going to be clicking and pasting some commands, if that's all right. So I'm going to be talking about how you assess if a resource is a good fit for your research project. All right. So those criteria would fall into 2 buckets. Those are the first 2 bullet points I have there. How do you get quick GPU access to get started? You get your initial results, to run your proof of concept jobs, and just to make sure that the basic plumbing is working. And then there's a other bunch of criteria. That is, okay, after you've done your gotten your initial results and you want to scale up your throughput by a factor of 10x, is this resource going to is it a good fit for your project? All right. So I'm going to talk about the quick access first. So for the Slurm nodes, the quick access partition and queues you want is what I show here. All right. The GPU partners and the quality of service is short GPU. Over on the LSF side, so we have most of the GPUs are still on LSF, LSF nodes. The high availability queue you want to target is the short GPU queue. Okay, so at in our documentation, on the bottom right, you'll see a chatbot. And you can ask that chatbot for this information. All right. So that chatbot is based on a RAG that's being updated every 24 hours. So as we update our online documentation, we're including resources, we're changing configuration, that RAG is going to be updated, so this chatbot will give you the current information. So that chatbot itself is an important part of the quick access story. All right. So let me demo that for you. That's why I don't have presentation mode. I want to actually be able to copy and paste these commands. All right. So on the Slurm side, so we have about 120 or so late model GPUs and more coming on the way. Here you can see on the Slurm side, we have 4 available L40Ss, some L40. So we see quite a bit of availability here. All right. So let me try to grab one of those. SALAC. All right. So let's see. We're going to try to grab 2 of those L40s. All right. You can see here I'm using, like I said, this partition and this quality of service. All right. So getting right in, we're on GPU 14. All right. So here you see this is GPU 14 here. So if I did that command again, SI nodes GPUs, you'll see that now turn to 0 because we're on it, right? There. GPU 14, right? That was a 2. Now it's 0 because these 4, now it's a 0 because we're running there now. Okay. So now let's look over on the LSF side. Like I said, the short GPU queue is a high accessibility queue. Let me show you what that looks like. So here shows the details of that queue, and these are clusters of GPUs. The largest one is this group, GPU underscore L40S. There's about 60 GPUs there. H100, H200, some more H100s, and so on. Let's look at the largest group, see what the utilization there is like. All right, so that gives you a picture of what's happening. So some of these down to maintenance, you can see pretty high utilization. Let's check out the H200. Down for maintenance probably. And the H100 is open. Let's check the other H100. Okay, 2 more H100s. All right. So that gives you an idea how to grab these things quickly. Now I am going to do the same thing I did on Slurm. I'm going to grab some of those nodes. Right. Look what I'm doing here. Right? I'm trying to grab one GPU. I'm going to grab it exclusively. All right. So only I can use that. I'm going to be the only user on that GPU. And here I allow a choice, right? L40s or H100 or H200. Let's see. Okay, so that looks like an L40S. All right. So there I have it. All right, so there's our one GPU. Okay.
How many hours the short GPU? I mean, we didn't catch how many hours the short GPU. we can.
Yes, so the short GPU queue has a time limit of 2 hours. The non-short GPU queue have a limit of 3 days. Okay. So the time is limited because it's a partner's queue. So the partners have to have priority. And they get that priority by the 2-hour jobs dropping off. So there's going to be a high upper limit of how much they need to wait for a GPU. As you can see here, it's going to be typically 0, right? But even on very busy days, at most maybe 15 minutes. Okay, so quick access. So this is our utilization growth over the past couple of years for research projects. You can see a 5x growth recently, but the one I really want to draw your attention to is this plot. That was research utilization. This is coursework utilization. That is a 2 order of magnitude increase in GPU use by for coursework. And I'm going to discuss some of the reasons for that. That was quite shocking to me when I saw it. A couple of reasons for that, and some of these relate to the quick access category I'm talking about. So we have open on demand, all right? And with this, you can actually integrate your research or coursework applications into open on demand. I'll show you that. So here I've logged into open on demand, and here you can see these applications. So some are available to everyone. RStudio, statisticians like that. There's a couple of courses use that, and Jupyter Notebooks. And then some research applications. This is a biochemistry cryo-electromagnetism application. It's integrated into open on demand. And when you access that, only people in that research project can get access to that. Let me show you what that looks like. Okay, so researchers in that group can log in and use that app, and it submits jobs to GPU compute nodes in the back end. Okay. And then, of course, there is logging in. All right. So the good thing about logging in with Open On Demand is that if your browser has your credentials, say you've checked your email already for the day, you can get right in without a password. Okay, and you can have up to 5 of these sessions open. The other nice feature is HPC VCF. Yes, please.
Speak on that, maybe you want to mention that just from the very start, getting HPC accounts free for faculty, and then they can have their graduate students and postdocs for free.
Yeah. Why don't you want to sign up and just say that? Jonathan Cranford.
Zoom.
You got to be close to the mic.
And probably have to be.
And
The mic is very sensitive. You can see anywhere. Okay.
Well, anyway, I'm here at the mic. I'm Andrew's colleague in HPC support. And I just want to quickly mention that getting HPC accounts free for all faculty. And once the faculty member has the account, they can add their research graduate students and postdocs for free. I just wanted to
Make that clear.
thank you.
What?
Where?
Mm-hmm.
How about research staff who are not faculties?
Research staff who are not faculty. Well, I think that's a gray area. I think you can just ask us.
Are you associated with a faculty member?
No, I'm with the research institute here.
I don't think that's an issue.
Yeah.
Just
Yeah, I can just email. Thank you.
ask us. Yeah.
I think if you just contact us, I think we have some,
Yeah, we have several staff people that have research projects. Okay. HPC VCL. Who has heard of this? The HPC VCL. Nice. So you can think of it as a login node that's exclusive to your research group, your class, or yourself. All right. And you can run, for your research group, for example, you can run some services on it, like an SQL database. I use it for that, for my class, or some kind of RAG or an agent or an LLM client, or any service that you want to be available for everyone in your group. Okay. And that CryoSpark application I was talking to you about, where that group integrated it into Open On Demand, that is running on a long-term HCVCL server. Right. So if I go to the VCL page, there it is right there. Okay. That application is running on that. Okay. I'll just quickly mention to teach, you just send us the course ID, and we have a special set of projects, class projects, where the file wiper won't touch it for the whole semester. Only a month after semester is done. So all those things contribute to, I think, why we have such a big jump in course utilization. So switching over to I call it the 10x stage of your project, where you want to ramp up your throughput 10x. What you need to look for and see if this resource is a good match for you. Main thing is current capacity and growth projections. So right now we have dozen each of H200s and H100s. We have 60 L40Ss and about 20 ampere class. Now, as you can see, we have a lot of congestion, but we're still able to get, on both Slurm and LSF, we're able to get GPUs. And this is Wednesday at 10 a.m. So this is very high utilization time. But what's so exciting is on the loading docks right now, getting ready to be installed, we have 8 H200s and 16 L40Ss that are going to be coming online very soon. We also have, in the next 6 months, 24 Blackwells. And within 9 months, we have 72 A100s coming. Okay? So very excited about that.
What's the difference that 600 Blackwell compare A100 or H100? This is a better one or similar one?
So these are newer. The Blackwells are newer.
This is a B200.
These are, yeah, the Blackwell, the B class.
Oh.
So the regular Blackwells are water cooled, but you can get these air cooled models. But they're enterprise grade, but they put that RTX in front of it. But these are enterprise grade. So Blackwell is the newest. Hopper and the L40S are about the same, and then the Ampere class starting to get a little bit old. But they're still very powerful. I mean, these things have like something like 40 VRAM. And an excellent double precision performance, great for scientific computing. Okay, again in the 10x category, sustaining high throughputs for the next 2-3 years, duration of your project. You also want to consider the integration with core facilities. All right. I'm just going to mention 2: research storage. That's very important for your workflow. It's a separate service from the HPC, but it's completely passively and seamlessly integrated into the HPC. And of course, as I mentioned, the HPC VCL. Right? Okay. So now I'm going to do a little demo on using Claude on HPC VCL. I think this demo showcases some of the things you can do with HPC. So I have a Claude client running on HPC VCL, and this is where you want to run. You don't want to run it on a regular login node. And it's going to look to the left to Claude Cloud, which is how people usually use it. And it's also going to look to the right where I have a SGLang LLM server running. All right. So I'm just going to, this is the same thing as showing you a little more detail. I'm going to have 2 terminals open. Top terminal, where it points to the left, and the bottom terminal where it points to the right. All right, so let's see how this works. Okay. So this is my top terminal. So I logged into the HPC VCL there. All right. And I run Claude. How am I doing on time? Do I have 10 minutes?
Maybe 5.
5?
All
All right. Let me try doing 5. Okay. All right. So this is pointing to the left to the cloud. All right. And this is my SGLang server running here, right, on GPU 16. Okay. So I was going to do some things here, but in the interest of time, I'm just going to skip that and run and go right to the local part. So the key to pointing it to the right locally is these 2 environmental variables. Okay. Let me see. Unfortunately, that line is broken up. I'm going to have to do this in pieces, probably in my history. Yeah, it is. So these 2 and 904. All right, so now it's going to point to the right. Now, one other thing I need to explain. The Claude Code client uses Anthropic API endpoints, but the SGLang server expects Open API endpoints. So I need a translator. All right, and that's what this is here. This proxy 5.py. All right, so I'm just going to run that. First, make sure that there's nothing running there. No typo. Okay. I'm going to talk a little bit more about this. All right, that's a good sign. Okay, so now I run Claude. I've done all of this. I've done those two things. All right, so it's warning you that it can go in either direction. The API key set to dummy is going to take precedence. So what I have here is I'm going to fix the spelling in this file. So the file text.txt has a spelling error. Fix the spelling error in the file text.txt. It's reading the text file. And there you can see the local servers responding. So we know it's going to the right place. And it's telling us, prompting us, do you want to fix this? I say yes.
Great.
Great. GPUs are great. So let's see if it's fixed. There, all right? It's fixed. Okay. One more minute. So this is, I'm just going to talk about how you set this up yourself. So two things. The first thing is I ran a proxy. I call it, proxy5.py. That's very limited. What that proxy does is it works with the Claude Code tool that just reads, edits, and writes a file. That's all it does. It's a simple 50-line thing. Now, if you want to set this up yourself so that it's similar to Claude Code Cloud Performance, you're going to want a proxy that can handle all of Claude Code's tools. So to do that, what you want is light LLM. All right? So that's the one thing you do different. The other thing you do differently is maybe a model. So the model I use here, right, is the 70 billion parameter model. It's about 140 gigabytes of RAM. I used it on 4 H100 GPUs. And it's okay with the Claude tools and light LLM, but it's not great. You really want to use one of these other models that I mentioned, right? Now, this one's interesting because it can fit on one of our H100 nodes. And that together with light LLM will give you local Claude performance that's very close to what you get on the cloud. And one of the ideas I have a node with 4 GPUs. I'm actually thinking of services to provide campus like NVIDIA digital twins or something like that. I'm thinking of actually putting this model on it and making it available. It's an idea. And that's the end of my demonstration. Any questions?
And Matt, just
Oh, yes.
you were just accessing Claude from a Hazel login node and not VCL.
And not?
VCL.
No, I was accessing, yeah, okay. So the top and bottom terminals are the HPC VCL. That's where I'm running the client. And this one at the side is I'm just monitoring the LLM job.
Okay.
And I do not recommend running Olama. Olama is very popular. It spins up very quickly. I do not recommend using it. I recommend the alternatives like SGLang because Olama, yes, it's great to get started with, but it does not handle concurrent requests well. If you have two or more requests coming at the same time, it can crash things very easily. Yes. Question back, yes.
Okay, so just a clarification. What we are doing here is we are using cloud code, but we are not using the cloud model. We are using a local model hosted on HPC to drive the cloud code. Right?
Yes,
Okay.
yes.
Thank
If you may have an interest in not having your information going out there or running out of tokens.
Thank you.
Okay. Great.
I have a question.
Yeah.
So Light LLM is already on HPC installed.
Pardon?
Light LLM is already installed on HPC.
You can install it yourself.
Okay, so this is so long if I wish I can do it so long.
Yes.
So eventually the ideal is HPC we can install some popular one like Python package. Then people you can give an access point. People do not need download, install their own every time.
Right.
You can just access, to open new session to use it eventually. Yeah.
Yes, and like I say, it's something that can be integrated into Open On Demand.
Yeah.
Okay. Cool. Thank you, Andrew, again.
Because we have 106 participant registered and maybe 60 or 70 people never use HPC. So this today for them a little bit more, but if you go to HPC webpage, you can know how to register, how to get the permission to access, and you can follow some of that. Yes.
We will also circulate all the slides that we're using today so that everybody will have contact information for folks who are speaking. And if you have questions, please feel free to follow up. And so with that, we'd like to welcome Paula from NC.
That's what I want. All right. Well, good morning, everyone. I'm Uspala, and I work with Duke Research Computing as an engagement specialist, and I'm also on the engagement team of NC Share. So great to be here. And today, what I'll be talking about is what NC Share can offer researchers across North Carolina, including researchers here at NC State. All right. So show of hands of folks who have heard of NC Share before. All right. So there's a few. Who has an NC Share account? Okay. There's a few more hands in there. Okay. So what really is NC Share? So NC Share is an NSF-funded coalition of 9 partnering institutions across North Carolina that aims to provide high-speed network for research purposes and also support HPC and GPU access. And the whole goal is to boost research and education across the state. And we recently got our 22nd member, which is Western Carolina University. They joined about a month ago. So this is a brief history of how NC Share got started. So around 2023 and 22 and 23, the Science DMC was established. So what this is it's a research network or a high-speed research network that allows to bypass like extra security features through networks. So think of it as the HOV lane of an interstate. So when there's heavy traffic, if you're on the HOV lane, you can have kind of like VIP access. So that makes research workflows much faster. So alongside this, we also established this authenticated federation. So what that allows is anyone in a North Carolina institute can use their home institution credentials to leverage these resources. So around 2024, we started CAS, which stands for Compute as a Service. So this is the second NSF grant. So this allowed setting up an HPC with compute nodes. So we have 8 compute nodes for researchers to access. And there were a few more nodes allowed for container managers. So that's kind of for like coursework, and the other ones are for research. So the cluster was set up, and this allowed like scheduling through the Slurm. And more recently, in 2025, with the third NSF grant, NC Share was allowed to able to set up the GPUs. So we have 32 H200 GPUs across 8 nodes. And then we also got more partners involved, and NC State is one of those partners. So through this partnership, we're providing all these CPU and GPU resources for 22 institutions across North Carolina. And how do we provide fair access to the GPUs? We have an allocation system that's set up. So I'll talk a bit about that later. All right, so we've had a pretty good growth. So around the same time last year, we had about 40 or 55-ish users, and within a year, we've grown up to about 460. So within a year, we've become pretty popular. All right, so apart from providing compute sources, what does NC Share do? So I'll share some of the activities we do. So we do these site visits where we go to institutions across North Carolina, and we talk to researchers and IT teams in those universities, and then ask them like, hey, like, what do you do for research? What are you lacking? And how can we help provide you resources through NC Share? So this was a site visit at UNC Wilmington last year. So we got to see all the cool marine research they do. And then we onboarded some researchers that are currently using the NC Share resources for their marine research. We also help organize and host workshops. So this one is a hybrid cube materials theory training workshop. So for materials theory simulation. So this was a multi-institutional collaboration between Duke, UNC Chapel Hill, and NC State. We had about 70 participants, and they used custom Aptena containers and multi-node MPI jobs through Open On-Demand and so on for this workshop. All right, so we also do these more like non-technical kind of workshops. So this one was a spring workshop this year. The goal of this was to kind of get a lot of researchers together in one room and then share the research that they do with the help of NC Share so that we can kind of like foster these interdisciplinary collaborations. Okay. All right, so we also provide summer internships. So this is an internship through Duke. However, with NC Share sponsorship, we're allowed to have a few students from institutions across North Carolina. So for this project, which is about gamifying research efficiency, we have students from Duke, NC Central, and also NC A&T through NC Share. All right, so that was kind of like the services we provide in terms of the non-compute stuff. So this is a slide about the NC Share HPC cluster. So as Andrew mentioned, it's very similar to like any kind of HPC cluster. So you'd have a login node where users would either SSH or you can log in through like a GUI, like Open On Demand. And then through the login node, you would access the Slurm scheduler that allocates resources based on availability and priority and so on. So we have two different types of compute nodes. So ones are the CPU-only compute nodes. So we have 8 of those, and each of those have 128 cores and 512 gigs of RAM each. And then we also, with the more recent gas grant, we have 4 GPU nodes with 8 GPUs each. So that totals to 32 H200 GPUs. So these are kind of state of the art. So we got like 141 gigs of VRAM on each, and then each of these nodes have 2 terabytes of RAM. So in terms of storage, so each of these compute nodes, they have a low latency NVMe scratch storage. So that's like high I/O. And there's other storage. So there's work, which is kind of temporary storage that has a 75-day purge policy. And then for more persistent storage, we have home and then data for kind of like a group shared space. I'll talk a bit more about storage and all of that in a later slide. All right, so how do you access NC Share? So anyone in North Carolina who has a North Carolina institutional credential can create an NC Share account and log in. It takes literally like 5 minutes. So we have a user guide, and then there's a page that tells you how to sign up. So as soon as you get an account, you can go to Open On Demand. That's like the GUI access to the cluster. And then if you want to access the cluster through a terminal, then you can set up SSH keys. So that helps you because you don't have to remember your passwords anymore. So NC Share doesn't really actually have any passwords. So once you...
So to correct that, they still need to throw their campus representative to...
Not for the first part.
Oh.
So the campus representative, like Derek, so if you want to access, so this is for the CPU. So as soon as you create an account, then you can access the CPUs. However, if you want to access the H200 GPUs, then you talk to Derek, and he would add you to the NC State GPU accounts. All right, so yeah, so this is essentially how you'd log in. So you can open up a terminal, SSH into this, log in with your user ID that you'll get after you create an account, log in through that, or if you don't like the terminal and if the terminal scares you, we have an option for that. We can use the Open On Demand portal. And then like both of those, they access the compute nodes through Slurm jobs. We have multiple partitions for different purposes. I'll talk a bit more about the partitions later, so that we have like common and interactive for the CPU partitions. And then we have 3 GPU partitions that you can access. All right, so yeah, so these are the partitions. So common is just for CPU only jobs, and interactive is for CPU only jobs that are just for 1 hour. And then we have the general access GPU partition. So that gives access to all the 22 institutions across North Carolina. So this is preempted, which means the jobs are going to be canceled and requeued for jobs that are submitted to the higher priority partitions. So interactive GPU is very useful. Say you want to do some debugging. However, you don't want to submit it to the GPU queue because there might be a longer wait time. So what the interactive GPU partition is useful for is if you want to do like quick debugging, you can get a job that has to be less than 1 hour, and that has higher priority than the GPU partition. So you would get access to the GPUs much faster. And then like GPU high partition, GPU HP partition, or the high priority partition. So you guys are lucky because you're a partner institution. So you have high priority access to the NC Share H200 GPUs. So there's a monthly quota for each of the high priority institutional quota accounts. And then once you exhaust that, then you can go back to using the regular general access GPU partition. So there are some other partitions like workshops. So that's for workshop support. It's like temporary. We'd carve out a node when there's a workshop going on. And then NC Share is part of the Open Science Grid. So that's kind of like a national pool of HPC resources that people can tap into. All right. And each of the GPU partitions, they have a GPU per user concurrent limit. And to talk a little about the NC Share storage, so there's 4 main storage locations. So each user, as soon as you create an account, you get 50 gigs in this home space. So that's useful for if you're like creating your or keeping your scripts, your applications, and all that. And then we have work, which is a much larger space. So that's good for like when you're dumping your calculation data. But the only thing is like you have to be careful because this is a temporary storage that's purged every 75 days. Or like the files that are older than 75 days are purged. And then if you want some shared space for your research group, then you can have some space under data. So that's accessible through like your PI and the institutional contact that can request leadership to get some space there. And then finally, we have the node local scratch space. So that's like high IO, and that's only within a node. So once you start a Slurm job, it gives you this, and you have to move that data out of the node, because once the Slurm job finishes, that just gets purged. Okay, so work versus Scratch. So why is Scratch important? Now, this is a quick benchmark just to show some numbers of read and write. So if you look at work, so this is to write 5 or 64 megabyte blocks, and the total size is 512. So if you look at the numbers here, this is if you want to write the same amount of data to work, it's like 247 megabits per second, but with Scratch, it's so much faster. So it's like 1.4, and then the read speeds are similar. But when you look at creating a lot of files very fast, so these are I think 1 byte files, and if you're writing 1,000 files at once, if you're writing it to work, it takes about 3.79 milliseconds per file. But with Scratch, it's like much faster. You can see it's like millisecond, like 0.02 milliseconds, and it's the same for read as well. So why is this important? So this helps avoid this thing called GPU starvation, because with the GPU CUDA cores, they process things much faster sometimes than what the data pipelines can supply. So if you're using just work with your GPU pipelines, that might starve the GPU. So use Scratch instead for cases like that. All right, so this is the graphical interface I mentioned earlier. Andrew showed this on the NC State side. So this is open on demand, so you can access apps like Jupyter Notebooks, RStudio. So on the right side, you see the panel. So you select what partition you want. So the QoS, it's normal for like all partitions except for the high priority, because the way we keep the quota billing is through a QoS. So you just request what kind of resources you want, and then like you'd get an allocation, and you can open up a Jupyter Notebook like this and then do your Python workflows and so on. So and for people who are kind of a bit more advanced in terms of like terminal usage, so you can log into NC Share through a terminal. So this is what a terminal would look like, and then it would give you some information about the storages and all that, and you're putting in a login node, so you can compile your codes here. Then once everything's set up, then you can submit a bash submission script requesting for the different resources you want. So in this case, you're submitting to the GPU partition. You're asking for 2 nodes and 16 tasks per node. Then you're asking for one H200 GPU per node, and then the time, memory, and then you'd submit the job with this batch. Then you can track your progress with the SQ. And if you want an interactive job through the terminal, you can do something very similar. And then instead of like submitting the job, you just do srun, and in the end you do like p2i bash I. So that gives you access to a compute node through a terminal. All right, so now let's talk a bit about GPUs. So like why GPUs, right? So I mean, like why can't you do stuff on CPUs? So CPUs are really cool when it comes to performing like really complex tasks. But if you have repetitive tasks, then you can use GPUs, because those have like thousands of cores compared to a CPU which have like 46, 64 to 128. So this is super useful for applications like AI, because AI uses a lot of like linear algebra and matrix multiplications. All right, so like this is kind of a comparison of the VRAMs of the different, like the popular GPUs that we have out here. So you can see like A5000s, A6000s, they have like 48 gigs of VRAM, but H200s are like, it towers off those else. Like the H100, I think, is 80 gigs, if I remember correctly. So that's around here. So like that's why the H200s are so popular, especially like with LLM modeling and like machine learning training and so on. All right, so this is just how it looks like when it's set up. Can anyone guess how much? So this is, I just got this from the internet. So this is an H200 node with 8 H200 GPUs. Can anyone guess how much this costs? Like a ballpark figure.
Each is
No, the whole node, like an H200 GPU node.
With or without academic discounts.
Just if you can like pay with cash.
1.5 million.
Less. Yes, like around that. I mean, it's more expensive now, but like close to $500,000 with all the stuff. So yeah, so the idea is like it's expensive, right? So I don't think you can like go to Best Buy and buy one of these. So that's why shared compute resources are kind of important. So I won't go too much in detail about. So these are some of the applications that researchers are using NC Share for. I would say right now like 90%-ish of the users are doing this, like model training with AI. So this is essentially, you know, like you have like your data, you're training it, and you're doing an optimization problems where you vary the weight to minimize the loss function. So very popular application. So once you have the model, then like Andrew was mentioning, you can use tools for inferencing, and even taking it a step further, you can use like these even like local models on an HPC to do agentic AI tasks for like Claude, open code. That's my favorite, by the way. All right, so yes, there's other things you can do with GPUs, not just AI. So this is another favorite of mine because this is like my PhD and postdoc work. So yeah, you can do quantum material simulations with GPUs because again, like, you know, a lot of these involve doing these linear algebra. So this is called the Schrodinger's equation, and solving that helps you understand matter. And then this is a eigenvalue problem, and an eigenvalue problem is essentially linear algebra, right? So like I mentioned, you can use GPUs to do like really cool linear algebra applications. So in this case, there's libraries like CuBLAS, which takes BLAS and then does the GPUification of it. So that significantly increases the efficiency or the productivity of these calculations. So that's another non-AI use of GPUs. All right, so I mentioned that we set up an allocation to provide fair access to users to use the GPUs on NC Share. So this is how it looks like in practice. So we have I did mention an interactive GPU, but let's forget that for now. But there's two main GPU partitions or allocations that users can use. One is the high priority GPU HP partition. So that is for the 9 partnering institutions, and NC State is one of those. And then the other one is the general access GPU partition. So on the right, you see the monthly quota for each of the 9 partnering institutions. So it's like in terms of GPU hours, so you can have high priority access until you exhaust that, and then everyone else gets this general access GPU partition. All right, so cool. Like, okay, we have access to GPUs. Does that mean we should just run them wild? Probably not, because these are like really valuable resources. So we want to make sure that we run them efficiently. So when we talk about GPU efficiency, so there's 2 factors that we have to think about. One is the GPU core efficiency. So that's an indication of how much of like the CUDA, like in terms of the NVIDIA ones, like the CUDA cores are engaged in a task. And the second one is how much of the GPU VRAM are actually utilized for this task. So for instance, like if you're running an LLM model that only requires 10 gigs of VRAM, like, is it really efficient to use a 141 gig H200, right? So, like, yeah, that's something that's important that we have to look at into when we're running these GPU jobs. So there's a few ways of measuring GPU efficiency. Like the easiest one is real time. You can look at NVIDIA SMI and the output, like it tells you like with each GPU what the efficiency is. There's other tools like GPU stat. But if you want to look at the Slurm history, so you can use commands like saccount, and then that tells you your GPU and then the GPU memory utilization. All right, so there's some other tools. One of our colleagues, Joe Shambling at Duke, developed this Slurm GPU tool. So with this, you can like provide a username and then give a range of dates and then the name of the partition, and it gives you the GPU and GPU memory efficiency of all the jobs within that period. And then it also gives you a time-weighted average of your GPU efficiency that's calculated with this formula. All right, so if you don't want to do that yourself, like we send out weekly reports for all the users that use our GPUs. So individual users get their GPU efficiency, and then we also provide information such as like collectively, partition-wise, how good are users doing. So this is for the GPU HP high priority partition. So you can see that collectively people are doing pretty good with the GPU efficiency, like it's 96. Memory efficiency, not so much, but it's still pretty decent. And then we also have triggers. So these are automated emails that are sent out to users who hit this like low efficiency mark, and then they can like reach out to us and get help. How do I make this job more efficient and so on. So it's kind of like a communicative thing, like where we work with researchers and help them optimize their GPU efficiencies and the workflows. All right, so one more thing. So traditionally HPCs, I think NC State probably uses modules, I'm guessing, like with module load and all that, right? So with NC Share, because NC Share is kind of like a collaborative environment, it's hard to maintain modules. So what we do is we have Apptainer containers instead. So we can keep them in like a general location. So a lot of people who want to reuse, let's say like a Jupyter notebook for a specific research application, they can reuse it from a common location. So we also allow installing things through Python and Conda. So this is just an example of if you're running a program through an Apptainer container, how do you submit it through a Slurm job? So these are just the flags for the resource request, and you just like call in Apptainer exec and the name of the container. And the next one is just like whatever program that you're running through that container. So in this case, this material science code called FHA-AIMS. So you're running a MPI job through that. All right. So what did we learn? Or if you didn't get anything from the talk, just these are the key takeaways. So NC Share is a collaborative effort, and like it's only thanks to a lot of the different teams that help make it happen. And then we also talked about GPUs being scarce and contended resources and why it's important to use it effectively. So NC Share is free, so please start using it if you want to. So how do you get in touch? So the first contact person for you guys would be Derek. And then you can also log into our homepage. We have an email user guide. So there's a user forum if you want to have a community forum thing. We do office hours. The links. If you follow this QR code, then you can have all of this information. I think that's all I have. So yeah, thank you for listening. Oh, okay. So should I?
You just provide an answer to that.
Yeah, they can just reference that webpage. It says the user just how to basically how to create a Conda environment.
Okay. Yeah, it's in the it should be in the user guide. Yeah, but we're happy to help. Yeah.
Okay.
Thanks.
Full questions quick in the room.
Oh, yeah.
So how do we go about deciding what to submit on NC Share versus the NC State
GPUs.
You have preempted.
Yeah.
Yeah. Go ahead and cover it using the appropriate resource for your.
Yeah.
And I think Jonathan had a real quick question as well.
For me. So is it that any university in North Carolina can get an account on the NC share, whether it's a partner or not?
Yes.
And they can use CPUs, computers.
So anyone can use CPUs and GPUs. The 9 partnering institutions, including NC State, have higher priority access to GPUs.
But the users at the other institutions still have to get added to their own normal thing.
Yes.
Before they can use GPU. So it still requires an additional step of a person at your institution assessing your fit for NC share and adding you to their GPU associated group. So you'll be able to get access however you want, or you can self-service get access to the NC share system, but actually using any of the GPUs will require interacting with whoever is the service provider contact.
But it's regulated by somewhere from a university in Tennessee. Their authentication could get out.
It has to be North Carolina credential.
How about this? We let Derek go ahead.
Yeah, Derek probably has all the answers.
Thanks for getting to follow.
Yeah, thank you.
So today I'm going to be walking through the questions people just raised, which is where does NC share fit into the other GPU options that are available to NC State researchers? I'm specifically going to be focusing on the no-cost GPU options that are available, because those obviously are the ones that people are going to be favoring relative to NC share. There are, of course, cost options available, especially commercial cloud, but as we've mentioned, high-level GPU computing in commercial cloud gets very expensive very quickly. For a little bit of context, I'm part of the Research Facilitation Service. We are a joint collaborative between a couple different cross-campus groups, and our main goal is to help researchers connect with the resources they need to do what they need to do, especially in the realm of computing and data. We kind of fit in between a lot of different service providers, whether those are consulting services, places to store your data, ways to move your data, or places to actually process, analyze, do the cool computing stuff. This means we don't have any direct ownership over any of these resources, but we work closely with a lot of them. For instance, I am the primary service contact for NC Share at NC State. So I don't work for NC Share, but I am going to be your primary onboarding person for getting you connected to the system. But likewise, I work closely with NC State's HPC cluster and the folks that support it, as well as a number of other resources available. And so my goal here is to kind of talk about how NC Share fits in with the other options you have and help direct people to the resource that makes the most sense. So when thinking about using NC Share, it does bring a lot to the table. For one, it comes with no cost for pretty cool resources, which is a thing that you can always assume you're going to get. And because it's somewhat specialized with just H200 GPUs, you have a bit smaller of a user pool relative to the number of resources that are available in one sense, which I'll get more into later. But it does mean that if the correct users are on the system, you theoretically could have shorter wait times for cool resources. You also have fairly high resource limits, including both number of GPUs you can use at a time and amount of time you can run them. And they might be easier than some other systems for getting access to those kind of resources. Your access is not tied to being a funding partner or otherwise having an existing grant, which can be useful for instance, early researchers that are trying to perform some research that's necessary to get their next grant, and they need this kind of hardware behind them. And then because this is a relatively new resource, can't make any promises here, but there is some amount of flexibility in adapting or adding to NC Share to fit what you need to do if it's almost but not quite what you need for your specific research workflow. With more established resources, this can occasionally be harder. And of course, the biggest thing that it brings to the table, at least for NC State researchers, are H200 GPUs, which we have access to. However, while NC Share brings a lot of cool stuff to the table, I like to phrase it as powerful but limited. There are some key considerations that should be in mind when deciding whether NC Share is the right fit. It has 32 GPUs, but it's shared by a large number of institutions. So that number seems big, but isn't quite as big as it sounds when you think about just what NC State has access to, which is functionally 5 GPUs. Of course, this isn't, we don't have a specific set of GPUs that are ours, but of the 32, we have a relative share of 5 of them. So this is fewer H200s than are just on our cluster. So this is not like a massive pile of GPUs where every single person who wants a GPU, if they use it, will have, any reasonable amount of waiting time. These are specialized GPUs that are there for specialized workloads. And we have an institutional monthly allocation. It's a shared resource, which means that the GPUs being used by someone else aren't getting used by you and vice versa. And finally, because of the model of NC Share supporting a large number of institutions, there's minimal user support available for, I'm going to call this like the training wheels aspects of using an HPC cluster. There's Uthpala, and Uthpala is great, but there is only one Uthpala, and he can't help every single person who's trying to learn to use an HPC for the first time, or doesn't know exactly what GPUs are. So this is a resource that is set up for people who are comfortable in, ideally, an HPC environment, used to at least the idea of a resource request model and a job queue, and have already kind of tested out the baseline version of their workflow on smaller scale GPUs. Some important questions to ask. Can your workloads efficiently make use of H200 GPUs? H200s come with some specifications that I'll get more into later, but whether or not the specifications are something you can actually take advantage of is important. Do your workloads require resources that are not available on NC Share? For instance, if you need short-term access to H200 GPUs, but what you really need is a bunch of CPU cores to do a lot of your research, and you're just using H200s for a small part of it, it might make more sense to do it on something like Hazel that has both. And finally, does your workload require on-demand or inconsistent usage? If you need GPUs available for a research workflow that requires pretty quick spin up and spin down, and that requires that all the time, it might not be necessarily the best fit for NC Share, and there might be more on-demand resources that allow you to have constant access to maybe a lower scale GPU that does what you want, even if it's lower scale or lower tier of an actual GPU. And so as part of this presentation, I want to highlight some alternative resources that exist and kind of talk about where they fit in. We've already talked a decent amount about our HPC system. Another similar resource to NC Share is Access. This is also federally funded. Access is an umbrella that includes a number of sub-resources below it that are similar to NC Share in that they are institutionally hosted generally, most often HPC-style clusters, but they have specialized nodes available, they have GPU computing environments available, and they have cloud and virtual desktop interfaces for some of them. So it's a slightly different request model, where you do a small application that requires a 1-paragraph to 1-page summary of your research to get a certain amount of credits, and then you spend those credits on essentially GPU hours or CPU hours. So this is a kind of like I consider it a, complementary resource, where if you're needing something that isn't exactly NC Share, but you want additional resources to what you're able to find on campus, looking through Access is a good way to kind of take advantage of everything that's available. And it's something that you could talk to us at the Research Facilitation Service about. One resource in particular I wanted to highlight as a useful alternative for those whose research workflows need GPUs but don't need H200s is Jetstream. Jetstream is very similar to, if you're familiar with AWS, if you've heard of Lightsail or EC2 instances, it's essentially what you're spinning up on Jetstream. They're virtual machines or virtual desktops that can come with GPUs, including A100s, both spliced up and whole ones, as well as H100s and non-GPU instances. The request models are a bit different. Instead of putting your job into a queue and waiting for the resources to be available, you spin up your machine, and it is going to consume credits as long as it exists. So this means you could have a GPU that just sits around and does whatever you want, including nothing, all year or as ever long as you have credits available. Versus NC Share has a job queue, submit and wait for resources. In the high priority queue in its current state, that is a pretty quick wait, but the more people who get excited about it and into it, the longer that wait's going to be. And for the normal queue, it can be a bit longer of a wait. And one quick note I wanted to make, if your goal is running inference without spending tokens, rather than taking a GPU for that purpose, Jetstream also has a dedicated inference service where you can make API requests to, I think the nicest one they have is the new DeepSeek model. and it's hosted on their infrastructure. So if you have a workflow that needs to run inference that doesn't always fit well with the job submission model because you're holding a GPU for very inconsistent usage. So that's an option that you can look into. A quick breakdown of these kind of GPUs that I'm talking about. I'm saying a lot of like GPU model names. This could mean a lot to you or it could mean nothing to you. A100s are, as Andrew mentioned, becoming slightly older in terms of being the cutting edge, but they're still very impressive GPUs. They can have 40 to 80 gigabytes of VRAM. I've most often seen 40, but the 80s exist. They have solid memory bandwidth of 2 terabytes per second, so you can load things into the GPU pretty quickly. But they have that older Ampere architecture versus the H100s and H200s share the exact same underlying computational infrastructure, that Hopper architecture. The big difference between H200s and H100s is that H200s have a substantially more virtual memory, as well as a moderately faster loading in of stuff onto your GPU memory. So this means that workloads that require more GPU memory, otherwise they'd be broken up into smaller batches or require multiple GPU communications, might be a better fit for H200s versus ones that simply just need to take advantage of a high-end GPU but could fit onto an H100 will generally run about as fast on an H100. I like to think of it as, do you need a bigger boat? If you're whitewater rafting down a river, yes, you could potentially get a nice speedboat or a full aircraft carrier, but it's not going to work for your workload. You only need a little boat. Likewise, if you're on a family fishing trip and you take an aircraft carrier with you, everybody will look at you a little bit weird. But if you need to carry a bunch of planes somewhere and fly them around, sometimes only the best model will do. And so sometimes your workflow really does need an H200 to get the job done, as I think a couple of researchers are going to be talking about shortly. So we talked a little bit about the request process. As Paula mentioned, you can get the base level NC Share account yourself, just using your NC State credentials, but that doesn't let you use any of the cool stuff. The actual process for requesting access to the GPU groups is through a form that we are going to be putting up shortly that will be on this page. Currently, this page has some information about NC Share, but we're wrapping up some of the aspects, having a couple people run their eyes over the final version of the form before we make it available. But it should be up there within this week or next week, is the goal at least. The general process will be you request access, and it'll be describing your research and how you plan to use NC Share. As long as everything sounds relatively okay, we would grant you access to the normal partition, which gives you access to the H200 GPUs, but it's kind of a scavenger model, if this means anything to you. You use the resources when they're available, but if a high priority job comes in and is waiting for a little bit, it might cancel your job and then your job gets restarted later. So it's important when using this model that you build checkpointing into your workflow so it can pick itself back up at a later time. If you use the normal partition for a month and you use it efficiently, but find that it's insufficient for your needs, then you reach out to the Research Facilitation Service email and request access to the high priority petition. And the way that we're planning on setting this up, though we're open to input, is kind of like a pool of GPU hours that we'll grant you initially, where you will be able to use the high priority partition however you need to use it until you run out of GPU hours. Once you finish the amount that you've been granted, you'll be booted back to the normal partition, and you can request to be put back in the high priority partition, but it'll be an opportunity to evaluate the efficiency of your use and whether there are a bunch of other people waiting for the high priority. The idea is to slightly incentivize using the more normal partition when it fits and the high priority partition for things that are high priority. And when you request, you'll just include a summary of previous use. The request will roughly follow the model of the Access Discover allocation, in part because this means if you fill out the NC Share model and you want even more GPUs, you can also just send the same proposal to Access and you'll get access to a bunch of credits. It's just basically going to be between a half-page and one-page summary of your intended use. This form is intended for faculty or research staff that aren't under faculty, research staff, and postdocs. Essentially, if you have students that need to access NC Share, their faculty advisor will apply and include the students that they also want to have access to NC Share. This will just include a quick list of some previous projects using GPUs or HPC just to verify that you know what you're doing. And then if you're applying for, access to the high priority queue, a quick summary of your use. We've talked a bit about efficiency and using these efficiently. Obviously, as IT folks, we would love everybody to use everything with maximum efficiency, but this is research and we don't actually expect that to happen. So what we're talking about in terms of our actual expectations for efficiency, for the normal partition, so this is the one that doesn't use up our NC State's monthly credit portion, is 30% memory efficiency. So using a decent amount of that GPU's virtual memory at some point during the job, and 50% time efficiency. So half of your job at least is actually actively engaging the GPU. For the high priority partition, our thresholds are a little bit higher because you're using credits that other people could use for high priority jobs. So that's 50% memory efficiency. So it's actively leveraging an H100 in such a way that an H100 wouldn't necessarily get the job done. And 70% time efficiency. So you're efficiently using the resource. We acknowledge that experimentation happens, that some workflows are smaller and could benefit from an H200, but aren't going to take a large amount of GPU hours. So we allow some wiggle room for relatively infrequent or low GPU hour jobs. But in general, this is what we're establishing as thresholds for the expectations of overall average use, to align in part with what NC Share has put out, and also just to make sure that this generally is supposed to be, could another GPU do this job just as well? And if the answer is no, it'll probably hit these metrics. And if the answer is yes, it probably won't. All of this comes together into what our advised or suggested GPU computing roadmap would be. This, of course, doesn't fit everybody, but this is generally how we think of how to find GPUs when you're an NC State researcher. When you're in the testing and experimentation phase, obviously you can use a local machine if it has a GPU on it, or if you have a lab desktop or a workstation or something like a lab server that has GPUs on it. Great opportunity to learn, to test things out, to break stuff and build it back up. There are also GPUs, A100 GPUs available on NC State's VCL that follow a similar scheduling model to what I described in Jetstream. So that's request the resource for a certain amount of time. You get full access to it. Nobody's going to interrupt it. You can use it as efficiently or as inefficiently as you want. And similar kind of ethos, correct me if I'm wrong, Andrew and Jonathan, but for the lower tier models in HPC, those are a great potential opportunity for experimenting with GPUs and kind of, learning and fumbling and trying new things without taking resources that are in a high demand such that you have long wait times. Once you're scaling up, we have the NC State's HPC's short GPU queue that Andrew walked us through. A great way to take advantage of more powerful GPUs someone else has already paid for, but only in 2-hour blocks. So either be running jobs in batches that will take less than 2 hours or build checkpointing in. We also have Jetstream 2, which is a great opportunity for scaling up to A100s or H100s that you can have full access to, use as much as you want, shelve as needed, that kind of thing. Finally, when you're ready for the deep end of the pool, you can try out the NC State HPC Partner Program. We have options for partial partners. So basically you purchase part of a GPU. So if you have grant funds available, but not enough to buy a full GPU node yourself, you can buy, I think it's like a single GPU on a 4 GPU node or something like that. Or pay for temporary priority if you just need less of a wait time on our HPC. There are advantages to running on NC State infrastructure. It's already connected to research storage. You have this shared access to a large amount of storage that connects right back down to your machine. It has potentially more NC State scoped support available. NC Share is, of course, an excellent option for the deep end if you need H200s, and there are reasons that our cluster doesn't fit. And then, of course, other access resources are available that have high-end GPUs and more of an HPC style. Submit a job, get your resources, use them. I think I have 2 more slides. Yeah. So we're finishing up my talk. The key takeaways I want you guys to take away. There are no-cost resources that exist to power your research. Just because you don't have your own GPU and you don't have the money to pay for commercial cloud or don't want to go through the hassle of configuring commercial cloud to work for you doesn't mean you can't do really powerful research with really nice GPUs. They exist. If you need H200s, NC Share is a powerful no-cost resource that we're really excited for people to get into. But if you don't need H200s, there are other options that will have less competition for these high-end GPUs and might fit your workflow better. And of course, the Research Facilitation Service, or the RFS, is here to help you navigate this infrastructure, consulting, figuring out how to fit your workflow to stuff space, whether that's the resources I've mentioned or something else entirely. Some useful links that people can go to, and this would have been a great place for me to put a QR code, but I didn't. If you want to get started with Access, access-ci.org/getting started. I'll warn you right now, if you guys are excited about Access and you try to Google it, it can be difficult because it's called Access and so is everything. But Access CI generally gets you what you're going for. I'll also note that as part of my role, I have an access allocation that I can temporarily grant people access to. So if you guys want to test out the resources without going through the application process, that's something that I can accomplish. For NC Share GPU user info, check out the user guide at that link. If you want access to NC Share GPUs as an NC State researcher, you use our Go link, which goes to a page on our website, which will have a form that doesn't exist yet. If you need, or if you have questions that are specific to NC Share as an NC State researcher, like how do I connect my data that's on research storage to NC Share? Like what's an efficient way to copy it? Or I have this Slurm job. Is this a better fit for something like NC Share or Hazel? Then you can reach out and ask us directly through our Contact Us form. However, if you're asking more specific NC Share only questions, like I loaded this module and it doesn't work, or this container doesn't have the dependencies I need, how do I get a container on NC Share, or any other NC Share specific questions, you can reach out to info@ncshare.org. If you CC us via our group email, we will be kept in the loop, so you can do that as you see fit. But just as a note. I think that's all. Yep. That is all from me. We have, I think, 2 more short talks by researchers, and more is coming up to maybe clarify something I said wrong. Oh, great. So beyond that, I'll let Paul and Vladi take it away.
All right. So I'm a faculty at physics, and mostly I use my NC Share and I use HPC locally for serious scientific computing. I'm not using it for AI modeling, mostly for just high performance and high GPU memory, fast computing resources. Okay, so so what do I do usually with HPC? So one of these problems that I was working recently is I was simulating stochastic lines dynamics to study actually dynamics near a critical point. Okay, so this is one of these things I was working on recently. And for that, since I'm working in the phase diagram of, let's say, water or any other liquid of some sort, okay, I need to scan over the temperature range, let's say density, and different volumes. Okay, this is essentially what I do. Okay, but here specifically there is some more model, like theoretical model involved, so things are a little bit more different. But the most of the physics is the same. Okay, so this is where I have to perform the scan, and I have to perform the measurements, okay, in that system, and then collect the measurements and do some statistical manipulations with these measurements. Because of this nature of this, when I measure this or I work with this phase diagram, of course I need to collect a lot of statistics, right? And this is why my physics, which I need to do, is never really lives on a single run. Okay? As well as when I go in this parameter space of temperature, let's say density and volume, I also have to perform multiple runs, okay, and then collect it into some output. Okay, so my physics still live here in actual comparison and among many controlled runs, not only single run. Okay, and this is why I have 2 layers of accelerations here when I do my scientific calculations. So first of all, I run one single, job on the GPU. On the GPU. Okay, so where I use a 2D accelerator for my lattice update. So I have like a volume, and each point in this volume I have to simulate approximately independently. And for this, the GPU is fantastic. Okay, and then I go into the full parameter space where I'm changing the volumes, I'm changing the temperature and the chemical or density. Okay, and this is where I can run 10 to the power 30 jobs with different input parameters, okay, which I provide over here to one single job. And then I collect statistics and analyze. So I personally use Julia as a programming language. I find it fast and it's easy to introduce to students. It is very similar to Python, but at the same time, I find it way more faster than Python. At the same time, I would prefer C++, but I cannot torture my students with C++. So this is why it's Julia. So because then I can share my codes with students, and at the same time, it is reaches the speed of C++. Okay, so example of this life cycle. So I choose the somehow it's like never really. Okay, I choose the parameters. Then again, so if we are talking about, let's say, air in this room, I need to wait a little bit, evolve the system somewhat to simulate these configurations in this, or the air in this room. Then I perform the measurements in the times of this time series and the air in this room, and I extract observations. Okay, so and there are some scientific requirements that I need to do here. The thermalization, first of all, thermalization and measurement, the distinct stages. So I perform thermalization first, I save the data, next I read this data, in the other run, I perform the measurements. Okay? And this also helps me if there is some failure in between, my data is safe, I can always restart. So I don't, for example, if my measurement is failed, a measurement usually takes long time, or longish time, let's say 2 hours, and the job fails, and I lose my data, I can always start from the thermalized file and, and restart it. Okay. So when I submit 10 to the power 3 jobs, sometimes even more, and then Paula not have that. Okay, so my seeds for the submission must be independent. Okay, and here is the street which I use, that for the seeds I use actually the parameters. Okay, some mathematical equation for the parameters that I provide to those codes. But that's very important. If you submit without the given a specific seed, then it might actually run with the same seed, and you will not collect any additional statistics, and that the issues you might run accidentally when you do the jumps, when you do runs with many jumps. Okay, so I usually save configurations and everything after that many steps that I perform when I run my jobs, so that I can always restart. Okay, or if it's a failure, I can always come back and look at that. Okay, so a single GPU job is pretty simple. So it was already shown before, and here this is my approximately the parameters that I use for submitting the jobs. So in this case, I'm measuring susceptibility. I don't know, like say specific hit. Okay, and when I submit it, so this is my submission. Script susceptibility over here. I provide the mass, I provide the init, I provide the seed, and etc. 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 Okay, I always specify the output where my output goes and where my error go, because I want to inspect them quite often after I start this job. So in this case, the actual memory that I require is not significant. It's 8 gigabyte, but oftentimes the GPU memory that I need is insanely large. Okay.
So next, sometimes I do mistakes. Okay, and one of these examples when I do mistakes is when I submit something and it doesn't do what I want, right? So then 2 hours of wait, and it's saying 2 hours of calculations result in nothing. So, and this is why I highly recommend to use these interactive jobs, and which is on HPC on NC Share is a run --PTI, and I debug my jobs before I submit 500 or 5,000 of them. Okay, so and this I often use these interactive jobs for initial error checking and also for processing data. So I have enormous amount of data, okay, so which I would like to plot. Okay, and I can use these interactive jobs to play with the data, okay, before I actually put it into full production. And for full production, I will still require to have an actual independent HPC run, okay, but if I would like to actually see at least something before to commit to this full production, I use the interactive job. Okay, so I am working always from the terminal. Okay, so and I think that if you really want to get into high performance computing, you got to learn this. Okay, so and if you work with a terminal, you know that if you work from the coffee shop, which I don't, but if you work from a train or an airplane, okay, so you would like to have your session preserved if you lose the SSH connection. Okay, and that happens often, right? So, and this is, or for example, you go to work, you work on your laptop, you go home, you work on your home computer, right? And you would like to have the same session to work in. Okay, for this, and still working from the terminal. For this, you want to use the tmaps. Okay, what tmaps do essentially provides you a multiple window environment within the terminal. Okay, very convenient. And additionally, if your SSH connection drops, or you lose your Wi-Fi, this session will still stay on that server at NC Share, to which you can log in, again once you get the Wi-Fi back. Or alternatively, you can go to work and connect to the same session that you worked with at home. Okay, tmaps is a must, okay, and you need to learn how to use that. Without that, things becomes extremely complex. I don't know how it is right now at HPC. We didn't used to have tmaps. We have not. Okay, so we didn't used to have tmaps at HPC long ago. Okay, I don't know when, but I compiled my own. Okay, and I use tmaps at HPC. For example, I would like to have a submission script, and I would like to have just by it, like a split screen. I would like to see how my jobs start populating the queue. Okay, this I actually use tmaps, split screen, and I look at it. Okay, so the next thing which you need to how to transfer the data. I have so much data. I'm literally swamped. I mean, totally swimming in it. Okay, so I have 200 gigabytes of data, which I need to always synchronize and transfer. Okay, so oftentimes I would like to work on it in NC Share without even transferring, only because I have so much. But all of that sitting on the partition, which is first every so often 75 days. Okay, so I eventually need to get my data to my computer. Okay, so or to my server, and for this I use rsync. So everyone who works with a high amount of data need to know how to work with this command. It's the best thing you will ever learn. So, and this is one of the commands that I use here. I'm not showing to which cluster I'm transferring it, but this is approximately how it works. Okay, and this. Okay, specifically the parameter A is very important here to archive your data, so it will preserve the timestamps. Why I do not use SCP? Because if I would like to SCP everything and SCP copying 200 gigabytes of files wouldn't be a good idea to take care of. So we use rsync to check which files are updated and copy only those, right? Very efficient, usually takes no time. Some of the rsync parameters include, for example, delete. It will delete the data which is not on your machine which is on your machine locally and different from what it is on the server. So it will delete extra files that do not exist on the server. Okay? One has to be careful with that because the server might have already deleted the data that you already need. This purge time of 75 days expired, right? So be careful with the delete parameter here. Okay, so I actually looked into my history of the commands that I use on NC Share, and this was approximately 2,000 lines of history. So the command that I use the most is apparently watch. Okay, and watch command just watches the specific updates on the specific command that you specify after that. Okay, in my case, I'm watching, for example, that. Okay, so like I'm doing this. I'm watching my SQ. Okay, or I'm watching an update of the file or anything like this. Okay, so oftentimes I generate on our HPC, I generate a specific watch file. So, but let's not go there. Okay, so the next most often common thing that I use are interactive Julia sections. Again, this is just to plot for quickly play with the data or see if there are any errors. And finally, the 47 is sometimes I run SQ just a single time, okay, just to see a quick output. Most of the time I do use watch. Okay, so and this just shows that what I do usually is submit, monitor, inspect, correct, and resubmit, okay? And sometimes copying the data. Okay, so my current HPC or NC Share, in this case, submitter, is very different from what it used to be before. In the past, I was using just bash scripts, okay? It's just something very complex and very bulky. I totally switched to submission using Python scripts. Okay, first of all, my submissions becomes a little bit complex, only because whenever I submit some data, I would like to check if the files that I want to compute already exist. Okay, it is possible that I already computed them. Okay, so, and I don't want to recompute them ever again. How can it happen? For example, I submit first the grid of parameters that it is not, that is rough. Okay, but for example, over here, I submit some grid of the parameters here. Okay, but then I would like to refine the grid. Okay, and those points which already were computed, I don't want to recompute. And writing a Python scripts gives you a little bit more flexibility of checking if the file exists and skipping it if it is possible, if it is required. Okay. Again, oftentimes I do mistakes and I don't want something to be deleted. So for any submission script, I add a dry run, which does nothing. It submits nothing. It just tells me what it's going to do. Okay, and I recommend you to do the same. Okay, so most of the time, okay, I'm always computing something on HPC or NC Share, okay, on both platforms. And really it's became like a part of my, everyday life. So the things which are extremely important, and I would not be able to actually function with HPC are Tmax and rsync. Okay, these two things are extremely important. Additional thing that is very important for me is to have NVIM. Okay, on NC Share, I was able to just install it. I cannot do it on HPC. Because of the quota limits on the number of files in the home directory, and Vim has extreme amount of files, bringing it with which are like really is a couple of bytes, but nevertheless required. Okay, so and eventually I started working with the submissions because I have so many submissions. I started submitting my jobs not by manually or not by writing bash scripts, and I recommend you to do the same, is to actually write in a separate, like let's say Python or a Julia scripts to do these job submissions in such a way that they would be checking the pre-existing output before submission is done. And I think I'm done with this part, and I will take questions.
Real quick about the HPC hub quota. If you're installing something there, you don't have enough quota, you can get a user app space that has a lot more quota to install things. It's persistent and never merge.
Yes. Yes. Totally. So you
Okay, let's move on with a lot of time, and I'm going to do that. I'll do a very particularly, something I haven't mentioned yet. You share the screen. So we talk about HPC and also other MC share and the get stream 2 and get access many GPU resources. Actually, in my personal opinion, if you are a student, if you're teaching a course, or if you just begin to use the GPU, the best starting point is the Google Cloud. So I have, we haven't mentioned that. I just want to give a quick, for example, here, that's to work. All sample code, like Gentle AI for Science already sent the link to the chat room. For example, here, all sample, I try to accommodate all in a single GPU. You can run all of these on a single GPU. And for example, here, you just simple click and open that. And when you open this one, here, this is my personal Gmail. In my personal Gmail, if you check the runtime, they provide you free T4 GPU. The T4 GPU, for example, okay, I can connect. And when you connect, you can click, you can check the resources. So now it's still working. So now you see, that GPU is the very beginning entry level, only give you 50 gig. 50 gig is better than nothing. It's still powerful. You can run most of the work. And so, for example, here, even though you can try to fine-tune a small large language model, for example, if you go back to GitHub and here in this place, you can check like chapter 3 or fine-tune a small language model. You can run this as a T4 very easily. And the reason is not like the HPC or NTCL, you have to log in, you have familiar the Linux or Unix command line. This one you can see the result immediately in progress. And but of course you cannot schedule a job, right? But this is the starting point. Okay? So but if you are NC State, for example, in this case, you can try to get some Colab Pro, like for example, E100 high memory, see if I can try to get it. So if you try to connect that, and in this case, good, lucky. So if you check resources now, the GPU bumped to 80 gig. Wow, that's great. They mentioned it, E100 is a little bit old, but still very powerful. You can do majority of the AI or model works. And for example, here this is the one, and NC State, this is we can get license. If you have the money, as you can see, you can get a Core Pro. It's $500 a year. That's a very good deal. now I will practice one for my students because they can use very quickly, very easy, and they send it to you. And so about 1,000 hours, something like that. So this is one. But this one has a limitation. This is why we talk about HPC, why we need the NC share. So just want to quickly and why we need the HPC and the NC share. So for example, I'm writing a month ago. We prepared a proposal for DOE, a $5 million severe weather research center. And we want to propose something from a storm forecast in NC area. So, but can we really do that? So I want to give a quick try, the demo, to make sure we can really do it before we put it into the proposal. I'm very physical guy and, honest guy. Many people put it in the proposal, they cannot really do it. But anyway, the thing is, I need a HPC, I need the GPU to run the model to demonstrate we can do it. So here's the thing. So this model comes from NVIDIA. As you can see, they do a diffusion, and they have the two steps. The two step is kind of, they have a regression model, they have a diffusion model. And what they did is, let's just very go quickly. Here it is. NVIDIA trained the model specifically in Central America, Central US, United States. And he run 64 X100 GPU for 120 hours. It's about 5 days. 64 X100. Nobody have a 64 here, And but the thing is, their model worked well in Central United States, not in the East Coast. The East Coast, they had to retrain the model because the geography is different, the coastline boundary, everything you have to redo it. You cannot just use the model applied to North Carolina. So that's it. So as you can see here, and then can we do that? So we try to put in a proposal that we want to do that, but we want to demo we're able to do that. So this is our jump to the NC share. So what, as you can see here, that's their model. You can see in a central US area and Illinois, maybe Ohio, and Kentucky area. And this is the east border. And as you can see, Western Virginia, Tennessee, you don't have, they're not including North Carolina. And so I contacted the team. I said, do you know anybody already pre-trained the East Coast of the US? Like, nope, I haven't heard any group done that yet. Then, that's what I do. So we have to give that to NC share. We're able to use 8 at 200. And you can see now, instead of constrained by the boundary, you see the boundary here? Because I tried to simulate Hurricane Florence and Helene, see how the flooding impacted here. But then, the pre-trained model doesn't work. So we have to retrain our own model. So look at this. Now this is the primary result of the forest. So we are able to do regression and diffusion. Now, the diffusion is not perfect. And, I'm not going to detail about that, but you can see when we compare already, we are able to do it. Now I can include it in the proposal that, we are able to have the resources, facility, we have the skill, we're able to do that. If you give us money, we will improve that. That's more promising. And as you can see, we run a lot. And look at Helene, this is the result. And also, beyond that, not only the weather, the big challenge is oceanography. How we can do ocean circulation, ocean current
and ocean surface temperature. So that the people just come out with a regression model alone to get that kind of gross cost ocean surface temperature simulation and forecast. And you can see, then I apply the same technology over the NC share. And so now we can do a regression and also diffusion, like the diffusion one, to understand the circulation in our area. So that's as you can say why the NC share or the GPU can give you the edge. But the couple thing I want to end it here. So I just said not like regular, he used command line. I use FTP, try to upload the file, download the file, and as you can see here, the couple good thing I realized that if I run a job, because you use this H200, I can simulate North Carolina, the weather, 2.5 days. I submit the job. I know we can require up to 7 days, but my job 2 weeks ago, I even don't know that the GPU high priority. So I just use a regular GPU. And the job was disrupted. In the beginning, I said, why is disrupted? Like you resubmit? Because no, because the system automatically posts their job to give a priority to other people. Then when the available resumes your job, I don't worry about it. So the job hang around there. You're line a queue, then eventually finish your job. That's a great thing. Then I begin to create a small language model. I train the language model. That one even beautiful because I need to finish pre-training, then fine-tune, then do a little bit reinforced learning and low-rank adaptive training, step by step. It depends on I have to finish the pre-training. If pre-training, the first step, second step, third step. Last night, I just realized I can use independence, as an option. I can say, when that job finish, then start my job. When that job finish, then start the next job. Oh, that's, every day the learning experience. So, I think that's I want to share. So it is great. I think NC State, NC Share, HPC, we have research facility. They have great resources. And, it's just not always in you. If you are a student, there's no reason you can't play new resources. There's so many available. You just need to dedicate yourself on it. Yeah.
We ran out of time for questions. So thank you all so much for joining us this morning. We, as we've said in the chat, we will circulate the slides and the recording to everybody who's registered. If you could please fill out our evaluation form, it really helps us to plan and improve these sessions. And we will make all of our contact information available for folks who have questions. Please feel free to reach out. So you know, this is we've got information on
HCC research computing resources that are available here at NC State and the resources. Thanks again, and thanks again to Paul, to Paula, Patty.
We'll have the email if you have any questions.